Hello, everyone. Welcome back to Calculus 1000. I hope that you guys had a good weekend. Did you? Seems so. Okay. It's still, the weather is good, so enjoy it before it's too late. So today we are planning to do two more things to complete this limit business. One is what I advertised at the end of last session. We are trying to see what if quotient law cannot be applied. In other words, when we are working with fractions or quotients of functions trying to find limit, if the denominator has non-zero limit, we can apply quotient law. Go ahead, do it, done, yes? But in most of the cases, the denominator won't be zero. So things won't be that straightforward. And we will discuss the details of that. In particular, I'll focus on how to fix the so-called 0/0 indeterminate form. The other part is the squeeze theorem. I'm hoping that we will be able to cover it, do a few examples before you can go ahead and do more stuff at home. Any questions, any comments before I start? Okay, then let's go into it and start this. Okay, remember that, so I'll write down this thing again. So when you're working with the quotient of two functions, we saw that there is an interesting case when the limit of the denominator as x approaches to a exists and is not zero. So in all cases, we are assuming that f and g have limit, and we want to find the quotient of them. Now, if the limit of the denominator is not zero, we can apply quotient law, or I write, oh my God, Q law, quotient law, and go ahead and evaluate limit as the limit of the numerator over the limit of the denominator, as x approaches to a, as x approaches to a. That's the good day of Calculus 1000, when the denominator has non-zero limit. What if it has zero limit? So what if limit of the denominator as x approaches to a is 0? Now, there could be two different scenarios happening here. One, so case one, I will write this way. When you saw that the limit of denominator is 0, just make sure that I cannot anymore use quotient law. Done. We are dealing with completely new stories. Now, we will go, after we saw that the limit of the denominator is 0, we go check the limit of the numerator. If it is not 0, so now what we have, limit of denominator is 0, limit of the numerator non-zero. In that case, we have infinite limit, well, which is a special case of does not exist. So if this happens, numerator is 1, denominator, limit of numerator is 1, limit of the denominator is 0. In that case, the limit does not exist, but expectation is that you have to be able to go further and say more things. You have to be able to say it is infinite limit, and when it is positive infinity, negative infinity. So we'll see in examples how this comes up. Now, what if the limit of the numerator is 0 as well? In that case, we are going into a darkness of, oh, I don't know what does that mean. That's why we call it 0 over 0 indeterminate form. 0 over 0 is not an answer, is not the result, is not the value of limit. It just says that there is something confusing, there is something not clear happening there, and we have to fix it. And the goal today will be showing a few examples how we can fix that. Before I go ahead and write down some examples so that we can start doing examples, is there any questions, any comments for me up to this point? Okay, then let's start with this example. Limit of, oh my God, x squared minus 2x plus 1 over x cubed minus, x squared again, minus 3x plus 2 as x approaches to 1.
Approaches 2 or something?
Sorry? What was the question, sir?
X approaches 1?
As x approaches to 1, yes. One thing that I will ask you to do is I'll show you how to deal with this in detail, but one thing I want you to start studying this quotient, going through these steps. In other words, you would like to check first what is the limit of the denominator. In other words, am I allowed to use the quotient law or not? That's the easiest law in our hands, so better to check that. If it works, then we just go ahead and do it. If it is 0, then we cannot use it, and we have to figure out which one of those other cases happen. So I'll give you only 30 seconds to run this first step. In other words, you want to tell me which one of those 3 scenarios will happen in this case. Go ahead, 30 seconds should be more than enough. Sorry. So, when you are assigned such question, you have to start with the denominator. That's a key point. In this case, this is a polynomial, and I can use direct substitution rule and get, okay, this is 1 squared minus 3 plus 2, which is 0. Well, this happened. Means that quotient law, no quotient law. We cannot use it here. The second thing, once the denominator is 0, we have to go ahead and evaluate the limit of the numerator as x goes to 1. This is 1 squared minus 2 times 1 plus 1, which is 0. Now, I have the full story in hand. I don't have yet the solution for it, but I know that 0 over 0 happens here. 0 over 0 is not an answer for limit. 0 over 0 is not a number. 0 over 0 is the status. It's the most confused status ever. You just know that there's something there, and you have to now work and fix it. That's why I would never write 0 over 0 equals 0 over 0. This is wrong. This is bad writing. But, as always, I can use that equality, top of that equality as, okay, that's my newsroom, basically. I'm announcing that this is 0 over 0 case, and I understand that something is not right here. Now, how to solve this? How to solve this 0 over 0 case. This is, I believe 99% of you will say, let's do L'Hopital. But we are not yet allowed to use L'Hopital. Until chapter 4, you're not allowed to use L'Hopital. We don't know how to differentiate. We don't know how to work with L'Hopital. Then, yes, we have to go down, work hard to solve these 0 over 0 cases. In particular, here, what you need to see that, especially if you're working with polynomials, if limit of a polynomial x approaches to a is 0, that means that a is its root. Or in other words, if you factor out, you will find x minus a factor. If this is a, x minus a factor is what causes the polynomial to become 0. So let's do, oops. Nice. Okay. My camera didn't go off, so that's good. Okay, so limit, I am factoring out, and the goal is to factor out vanishing factors. What is vanishing factor? As if x approaches to a, x minus a is the vanishing factor. And, well, you just factor it. You will right away notice that you at least have one x minus, oh, sorry, this is 1. You will at least have one factor of x minus 1 in the numerator, x minus 1 in the denominator. But if you complete the factoring, you will see, okay, there could be, again, more factors, but that's the factor. We have to have that vanishing factor. So what I did, the first step is factor out the vanishing factor. The second step is cancel the vanishing factor. Aren't those things, those factors, the factors that causes the 0 appear in the numerator or denominator when we are evaluating it? Let's cancel them, because it's 0 over 0. You will have 1 in numerator, 1 in the denominator. When I cancel it, the remaining will be this. Wait a minute, how you're supposed to cancel x minus 1? How do you know it's not 0? Remember, we were very worried that you cannot cancel or multiply if your factor is 0. And the answer for that is, why I am allowed to cancel this x minus 1? Yes?
You don't care about what actually.
When we are studying limit of something as x approaches to 1, we study that function around 1, but never look at the value of the function at 1. So in this case, what makes this 0 is x equal to 1, but we don't care about x equal to 1 because it's x approaching to 1. X is not going to be equal to 1. Once you did factor, then cancel, you're going to get completely new limit, as we did here. Now, it's a quotient, limit of quotient. Then you repeat the same steps. Is the limit of denominator 0? Well, let's see. Limit of x minus 2 is 1 minus 2 negative 1. No, that's not 0. That's the best thing that can happen to us, because now I can go ahead and say quotient law, limit of x minus 1, limit of x minus 2. And these are just polynomials, yes? Can I maybe erase that piece there and just continue this? This is direct substitution again. And I get 1 minus 1 over 2 minus, sorry, 1 minus 2. And this is 0 over negative 1. That is 0. Yes, please.
Law every time, can we just use direct that it's not?
Well, yes, you can actually. You could have, that's a very good point. Remember that the direct substitution had a version for the quotients for the rational functions if the denominator doesn't have 0 value at that point. Yes, you could sign it that way and go ahead and evaluate that. Any other questions? Yes?
This question, we have to show our check for the denominator every single.
I think in some ways, all the work I'm doing there, I'm trying to provide enough evidence that I got 0 over 0. Yes? This could go faster or just show a small piece just to make sure that it is clear you're doing that work. Yes? Let me summarize what we did here. First thing is you should be able to identify which case happens here. In particular, if it is 0 over 0 indeterminate form, you have to announce it. You have to say, oh, look, this limit is 0 over 0. That's the starting step. Then you factor the vanishing factor. Then you cancel it. Or I ask like very quick version of that. Factor, cancel. This is how we will resolve 0 over 0 indeterminate forms until we learn what is L'Hopital. Does that make sense? So you do announce it, and then you do factor, cancel. Another time, you announce it, it is indeterminate form. Then you factor, cancel. That's the two steps that you have to repeat. And then you just go ahead and do more things. Let me write more examples down here. Limit of x cubed plus 3x squared plus x over x cubed minus 2x squared. As x approaches to 0, I have one more. Limit of root x squared plus 4 minus 2 over x squared as x approaches to 0. This one is very similar to what is happening there for that example. So I'll say you should be able to complete the steps, or at least a few main steps at the beginning of solving this example in less than 1 minute. For the other one, I'll just give you another 30 seconds so that you think about, oh, what is special about this? How should I start that example? And what is the best way to do the work on this very specific example? Okay, 90 seconds. It starts now. Feel free to talk to the person sitting next to you. Go ahead, please. So 50 seconds left. Okay. Okay. So the first thing is check the limit of the denominator. Direct substitution here gives me 0. Right away means that quotient law, we cannot use it. Then the second thing that when the limit of the denominator is 0, we go ahead and find the limit of the numerator. And again, direct substitution here gives me 0. So we saw that 0 numerator, 0 denominator limit. This means we are dealing with 0 over 0 indeterminate form. And we are writing it above equality just as a board to announce the situation. Yes? Now, in this case, what is the vanishing factor? What is the vanishing factor? Yes? Well, let's don't rush here. We said that if x approaches to a, the vanishing factor is x minus a. In this case, a is x minus 0, or in other words, x is the vanishing factor. And just factor this, you will notice that there is an x factor in the numerator. And, well, actually, there is x squared factor in the denominator. So we announced that it is 0 over 0. We factor it, and then we should cancel it. Yes? So canceling here, I cancel 1 from top, 1 from down. So I get x squared plus 3x plus 1 over x minus 2. Once you factor, once you cancel, then you have completely new limit. Means that you repeat all these stories over there. And for this specific case, let me put the line here so that these are not. Limit of x times x minus 2 as x approaches to 0 is 0. Limit of the denominator is 0. Then I go ahead, find the limit of the numerator. It is non-zero. So limit of the denominator 0, limit of the numerator non-zero. Then we are dealing with infinite limits. So if I want to be a little bit sloppy, I'll just do this. This is either plus or minus infinity. That already means that the limit does not exist. And also it means that, well, specifically I know that infinite will come out. But why I am sloppy here? Because I'm not carefully saying when it is going to be positive infinity or when it is going to be negative infinity. For that, I need to show a little bit of work. And this is how it will work out in this case. So the more clear way of doing it is, so I'm getting 1 over 0 kind of thing. That's definitely infinity. But I want to determine what kind of infinity. Is it plus infinity or minus infinity? Well, in the numerator, I have positive number. That's cool. This is 0 minus 2. This is negative. So this was positive. This was negative. It depends on the sign of x, meaning that when we are approaching to 0, are we using negative numbers to approach 0 or positive numbers? Well, both of them could happen. Indeed, we should separate this into one-sided limits. Now, let's look at this carefully now. As x approaches to 0, numerator is 1. That's positive. Denominator has this piece, 0 minus 2. It is a negative number, so this is negative. X itself, I'm approaching to 0 using positive numbers. So x is going to be positive. This is negative. Positive times negative is negative. So today boards are not good size for me. So I have numerator 1. Denominator is a small number, close to 0. But just based on the fact that this is negative number, this is positive number, I know that I'm approaching 0 using the negative numbers. So I have 1 over a number that gets closer to 0, but always gets negative values. So 1 over that is going to be infinity, but positive times negative, it is negative infinity. Same story down there with this difference that, now, this is positive 1, numerator is positive 1. This is negative because 0 minus 2, or closer to 0 minus 2 is negative. X approaching to 0 from the negative side. So this is negative this time. Negative times negative is positive. So yes, we are getting closer to 0, but we are going to have only positive numbers in the denominator. 1 over positive numbers, very small, it's going to be plus infinity. And that is the level of the refinement that you have to go. You have to show me that, yes, you see it is infinity, but I can't identify or clearly tell you when it is plus infinity, when it is minus infinity, or what else happens. Any questions, any comments? Well, then let's start working on this other example here. Before I start working on that, what is special about this limit that we didn't have in the other two limits? What was it? The square root. The numerator is not rational number. Sorry, it's not a polynomial. We are working with irrational number, irrational function. But before we go to the details, you can check the denominator, limit of denominator, limit of the numerator. By direct substitution, I'm not writing that part because I have been repeating that enough so that you know the complete work is that I have to go find the limit of denominator, limit of numerator, and so on. So it is 0 over 0. I announced 0 over 0. Now I have to factor, yes? Oh, denominator is already good, factored. Actually, it has x squared rather than just x. The vanishing factor is, again, x minus 0. And I have 2 of them in the denominator. In the numerator, it's not polynomial. I don't know how to factor out x there. And this is one of the steps that will help you to turn the numerator into a polynomial. Can anyone tell me what is the trick there? Do you remember? Yes, please.
Square both the numerator and the denominator.
Okay.
Into the 2.
You square both numerator and denominator? What was?
That a way to do it? Oh wait, no.
You're.
Sorry, you have to multiply it by x squared minus 4.
This is okay. Yes. So you remember that. Let me put the right word out there. To rationalize numerator, that was what you were trying to say, I need to multiply the numerator by its conjugate. What is conjugate? This minus that turn minus to plus. So I multiply numerator by x squared plus 4 plus 2. Wait a minute, you multiply numerator by an expression. So you changed our function. No, I will multiply the denominator by the same thing so that my function is not different. It's the same thing. So x goes to 0. How this is going to work? This works simply because if you have a minus b times a plus b, you're going to get a squared minus b squared. Now I have a minus b times a plus b. So my expression in the numerator will be the square root of x squared plus 4 squared minus 2 squared. Denominator, I'll just write as I see it. Yeah? A square root of something is squared, then square and square root cancel each other, and what we will get here, this guy, is just x squared plus 4. X squared plus 4 minus 4 is the new numerator. X squared plus 4, and then minus 2 squared, which is 4. And then we have x squared plus 4 plus 2. Yeah? Well, the numerator, you simplify the numerator, you get just x squared. Remember, all these things we did to be able to factor out the vanishing factor. Now, the numerator is x squared, the denominator has x squared, so we can cancel these two, and I get limit of 1 over root x squared plus 4 plus 2. As x approaches to 0. Yeah? Well, this is new limit. Limit of the denominator is not 0. Apply quotient law, apply direct substitution. I'm not writing all the steps now. I'm just jumping so that we can finish this thing. I'll get, including quotient law is applied here. It's going 1 over 4. I'm putting 3 dots there, meaning that if you wanted to show your complete work, you had to write few things there, yes? 1 over 4 is the answer for this one. Any questions, any comments? Yes, please.
Vanishing factor for that, whatever is canceled out, so x squared in this case.
A vanishing factor in general, when x approaches to a and makes your numerator 0 and denominator 0, the vanishing factor is this. Or maybe other powers of this, but you will have at least 1x minus a. In this case, a is 0, so we will get powers of x. Well, we found in both numerator and denominator 2 powers of vanishing factor. It happened to be like that. Okay? Did I answer your question? Okay. Yes. Yes.
After we plug in x equals 0 for x squared, for the root of x squared plus 4 plus 2, we get root 4 plus 2. Why did you take the positive for the root of 4?
Root 4. Is root 4 2 or negative 2? Okay, let me ask you this question again. Root 4. Is this true that I say this is either plus or negative 2? Somebody said no. Why it is no? Yes, please.
It's negative, then you can't have a negative square root.
Well, it is outside. This is outside. Well, I think this is the convention of the inverse of x squared issue. we always consider root to be positive number. Okay? So the correct answer is that there's no negative sign there. But, if someone asks you, what is x, that gives you, x squared gives you 4. In that case, you're saying that, okay, x is going to be either plus root 4 or minus root 4. In other words, the way this happens in the equations, to be able to cover all the possible things, we are adding that plus minus when we are solving equation. But root 4 itself, we have defined, or in the standard convention is that root 4 is always plus 2. Yeah? Yes, please.
So we just assume any number, the square root of any number is just positive, right?
We assume, yes, we assume that this is the very standard back there always happening. Square root of any positive number, we take it as positive. But plus minus comes out when you're trying to solve an equation like that. Okay, let me go. Now I won't be able to answer more questions because we need to start the other topic, which is called squeeze theorem. Or if you like, or you're hungry, some people call it sandwich theorem. And you will see why. Before I start that, there is a fact about limit and inequality. This is a simple fact. Well, proving it needs a little bit of work, but not very far from our intuition. It says that let f and g, let this inequality happens for two functions for x's close or near or around a. So you have two functions. When you look around one specific point, a, 0, 1, 10, you see that the values of this one function is bigger than the other one. Now, if f and g have limit as x approaches to a, so they have a limit, then as a result of very simple calculation, you can see that the limit of smaller function should be less than or equal to limit of the bigger function. Or, as I like to put it in this different form, is that limit respects inequalities. If a function is smaller than other one, its limit is going to be smaller than the other one. Graph-wise, when you look at a function like this is a, this is g, this is f, if the function is around a bigger than the other function, the values, the trend of values of the bigger function as x approaches to a is going to be bigger than the trend of the values of the smaller one. So limit respects inequality. For example, because of this simple calculation or simple fact, you can, for example, say that, limit of sine x as x approaches to a is going to be always a number less than equal to 1. And a number bigger than equal to negative 1. Why? since for all values of x, sign is between 1 and -1, yes? So I have considered these two functions. One function is smaller than the other function. Then that means that limit of smaller one will be less than limit of bigger one. No matter what is a. Or you can apply that fact again here. No matter what is a, limit of sine x is going to be between limit of -1. What is limit of -1 as x approaches to a? -1. Limit of constant, no matter what is a, is going to be that constant. So -1, limit of x approaching to a. Sine x, this is 1. Or you can show that there is no a such that limit of 1 over x squared plus 1 as x approaches to a is equal to 2. There is no value of a such that when x approaches to a of 1 over x squared minus plus 1 cannot be a. So this is for you. Do it yourself. Think about it. Try to see if you can use the inequality. There are more than one ways to do it, but if you can do it using this inequality inspection thing, that would be nice practice. So limit respects inequalities. Squeeze theorem goes a little bit more than that. It says, so this is the theorem, squeeze theorem or sandwich theorem. So let f, g, h be functions defined around a. So you have three functions that are defined around a point a. And you know that if evaluated at any of those close by values gets you smaller value than g evaluated, gets smaller value than h. For all x around a, for all x around a. And you know one more thing. You know that the upper function and the higher function, as x approaches to a, they have limit, and their limit are the same. So if I break it down, there are four things happening. One, we have this inequality. Two, function f has limit. Function h has limit. Their limit are the same. Then you can conclude that the middle function has limit as x approaches to a, And limit of gx as x approaches to a is going to be the same number. Not only it has the limit, but its value is going to be the same thing as the previous one. So what does this say is this, that we have three functions. Around a point A, they follow this inequality. F is less than G, and G is less than H. In other words, F and H bound the values of G. Now, if F and H, they have same limit as x approaches to A, they will squeeze the middle one, which is G, to the same limit. G won't have any other possibility. It cannot run away. It will squished by F and H, or squeezed by F and H, or sandwiched by F and H to the same limit. So whenever this happens, you have to, these conditions happens, then you can get simpler thing there. One thing that will come out here saying that, what kind of tool is that? Someone is asking us to find limit of the middle one. Now we have to find inequalities. We have to check limit of two bigger functions, smaller functions, and then be able to find one middle function. The point is that sometimes there's a very important example before you leave. I have to do this example. Sometimes finding limit of a function as x approaches to a is not possible by itself. But we can bound it by two easier functions such that they have the same limit as x approaches to a. Look at this function. Function x times sine of 1 over x. Oh, this is product of two functions. X sine of 1 over x. But I'm not allowed to use product law here. Why? Why? Limit of one of the functions does not exist. You can only do product law if both limits exist. Sine of 1 over x as x approaches to 0. Remember that oscillating thing? It never gets closer to anything. So sine of 1 over x does not exist, so I cannot apply product law. But what I can do is this. I can see that forget that there's 1 over x. Sine of any angle you give me, it's going to be between -1 and 1. Yes? It's always going to be between -1, including if this angle is given by x or 1 over x, doesn't matter. It's going to be still between -1 and 1. Now if I multiply both sides by x, so x times -1, this is going to be negative x. X sine of 1 over x. X times 1 is x. Wait a minute, I multiplied both sides of an inequality by a number x. I know that I have to check if it is positive or negative, yes? So I'll just consider that I am only doing the positive x's. If you do have negative x's, you flip that inequality, which gives you very similar inequality. But let's just consider this. Now, I see that for all positive x's, this is true. Do you see what's happening? x sine 1 over x is a complicated function as x approaches to 0. But x itself, or negative x, these are easier functions when we are trying to find the limit. Indeed, we know that limit of negative x as x approaches to 0 is equal to limit of x as x approaches to 0. Here it is 0. Sine x, x sine 1 over x is bounded by two other functions. The upper one and lower one have the same limit. Then the squeeze theorem tells me that the middle one should have the same limit as well. And that's the end of the story. Have a great day and see you all on Wednesday. Sorry about that.
I'm just going to come in at 12:20. I just am.